Hi everyone! In this video I would cover statistical quality control. We tried two different quality control methods in the lab, acceptance sampling and statistical process control. In the first method, you measure the length of 7 random rods from 2 boxes. Then you're gonna calculate the mean and standard deviation of those 7 parts. Using this data, you're gonna evaluate student t-test. Student t-test is basically a method that allows you to decide whether to reject or not reject a sample. It is not enough criteria to accept a sample, but in this experiment we're going to accept a sample if the sample meets this criteria, the criteria of a student t-test. In the second method, statistical process control, you measure the length of all 7 rods of one lot, then you repeated this for 3 more lots. Then you're gonna calculate the mean and range of those 4 lots. Then again you need to calculate the mean of mean and the mean of range, and then from this data you're gonna create a control chart. Now that you have this control chart, you can evaluate any other lot and the mean and range data of any other lot and see if the data fit into the control chart. If they fit, they would be accepted. If not, they would be rejected. Now, for the first method, student t-test. William Gossett developed this method as a statistical method with the name student t-test. He was a researcher working for a company, and the company was concerned about the secrets being released. So he published this method under the name student. So this method is known as student t-test. In this method, different hypotheses would be evaluated. The main hypothesis is called null hypothesis. And in this hypothesis for this experiment is that the selected sample doesn't have a statistically significant difference from the average sample of the company. And the average sample has the length 3.7 inches. So this is our null hypothesis. And we're going to try this student t-test to whether decide to reject this sample or not reject it. Suppose I have these 7 values for the length of 7 random rods for the first part of this experiment. First, the first thing I'm going to do is to create a frequency distribution chart. I would select this column, go to insert and insert a histogram chart here. You can format this horizontal axis. Adjust the beam width to 0.05. So I have this frequency distribution chart. It means that one of the samples is in this range, 3 are in this range, 2 this range, and 1 more in between these two, 3.88 and 3.93. And this blank area, it means that there is no rod with this length. So another thing I need to calculate here is the average, mean of these samples, and the standard deviation. For mean, I can use this built-in function, average, equals average. And for the standard deviation, STDEV. Now I have mean and standard deviation. I need to calculate t-value. Here's the t-value, mean minus mu sub 0, which in this experiment is 3.7. It refers to null hypothesis, and it is the average length of the rod, divided by standard deviation over square root of sample size. The sample size is 7 for this experiment. And then after you calculate t, you're gonna see if the absolute value of t is less than critical t or not. So back to my spreadsheet. Here I would calculate t value, which is equal to my mean. So I would put this inside parentheses. Mean minus 3.7 close parentheses divided by standard deviation over square root of SQRT of 7. So this is my t value. Now I need to find the critical t and compare it to my t value here. We have one-tail and two-tail student t-test methods. This is an example of two-tail student t-test method. So we have frequency distribution and we are ignoring the two tails because only a few of the samples are in this range. And these two values add up to 0.01, which is called level of significance. And this refers to the null hypothesis, which considers that there's no significant difference between our sample and the average sample. You can also ignore one of the tails, so that would be called one-tail method. Now back to my spreadsheet. Let me make these values consistent with the other, so in terms of decimal places. Now I have this t value that I already calculated and I need to compare it to the critical t. So our t value was 1.1. Now you need to compare it to the critical t from this table. This table is available in the manual and it is called t distribution table. You have different critical t for different significance levels and different degrees of freedom. You can find degree of freedom for your experiment by subtracting 1 from the sample size. So you have 7 samples minus 1 would return 6. So you need to consider these critical t's, and as we have the two-tail method and 0.01 level of significance, so this would be the critical t that we need to compare our value and decide if we're gonna reject the sample or not reject it. So as 1.1 is less than 3.7, we decide to not reject it. And as I said, the student t-test is not enough criteria to accept a sample. We just don't reject it. Another quality control method is to use operating characteristic curve to see if the sample size is enough to accept the sample or not. This operating characteristic curve shows the probability of accepting a bad box for different d values and different sample sizes. And this is for level of significance of 0.01. Now, how do we define a bad box? Suppose we want our sample to be within 0.15 inches of the average. If it is not in this range, it would be considered as a bad box. So here's how we calculate d, 0.15 in the numerator. Now for this example that I'm giving here, divided by s, standard deviation, and I calculated this for the 7 rods that we already studied, and I got this number, 1.11. I can find it in this curve. Now notice that as the sample size increases, the probability of accepting the bad box decreases. It means that as the sample size increases, we get more precise. So it's better to choose a larger sample size. And also as d value increases, again, probability of accepting decreases because we don't want this value to be a large value. Now we want to see if 7 rod would be enough sample size to accept this sample. So I would find this value in this horizontal axis here, and I would draw this vertical line to see where it intersects with this n equals to 7. So this corresponds to 65% of probability of accepting the sample, but we want it to be 0.15. We don't want it to be larger than 0.15. So if I draw this horizontal line for 0.15 probability of accepting, it is located below this curve, and it is located between n equals to 10 and n equals to 15. So the number of samples to be enough to accept this sample would be somewhere between 10 and 15, say 14. So this time I added 7 more samples and measured the mean and standard deviation, and again I calculated D and I got this number. So if I find this number in this curve, it would be somewhere here, and it would intersect the probability of 0.15 at this point, which would be located between 4 and 5 sample size. So 15 sample size is definitely enough to accept this sample. C method, you had 4 different lots and you measured the length for all the 7 samples in each of the lots. Now I'm gonna calculate mean and range for these lots. And for range, I have maximum minus minimum Now if I drag this autofill handle, I would have this for other columns. Now mean of mean would be mean of range. So I have these 2 parameters from this table available in the manual. You can find A2, D3 and D4 and plug into these equations to find lower control limit and upper control limit for mean and range. So you need to select these numbers because we have 7, the sample size is 7. So when you plot this, you would have lower control limit and upper control limit. This would be your control chart. Then you also measured for four more lots. So you would have 4 of these dots in this control chart. And considering these different zones, you can comment on how out of control is the process. So the closer to the mean of mean is better. So it is more probable to accept the sample, and the farther from the mean of mean is worse. So you had 4 data points to include here because you only measured for 4 of the additional lots. You can also do the same thing for the range and see if your data point will fit into this upper and lower control limits for the range. As I said, you would have only 4 of these data points because you only measured for 4 additional lots.